Okay, so welcome, Physics 1021. This is a very crowded classroom. So lots of people here. First thing I'll say is that MUN has required that everybody in the class wear a mask at all times. I do have to be a stickler about this. So if you don't have a mask and you're not wearing one, please do come up and get one. I've got lots of them right here. Okay, thank you. And if I notice masks slipping during class, I'm going to try very hard not to call attention to anybody, but I will pause and just remind people to lift it back up if it starts to slip. I know what they're like. We've all been wearing them for a couple of years, but we do have to follow the rules. So MUN has them in place, and there we are. So welcome to Physics 1051. Everybody in the right spot? I had a friend who sat through the wrong lecture because she didn't want to get up and leave. If you're not supposed to be in physics, you can go. Yeah, okay, super. So everybody's here and you're supposed to be here. I'm Kelly Shoreland, the instructor. We're going to do a quick run through the syllabus today and get started on a review of the last topic you would have done in Physics 1050. 1051 is a really nice course. We cover waves and electromagnetism. We kind of do the fundamentals of those. So if you're just looking for the fundamentals, you'll get it in this class. It's also a nice bridge for if you're going to go on in physics or maybe on into engineering or something like that. So 1051 is a good class, and I do hope you're going to like it. So this is how you can find me. My office is in this building upstairs, room 3058. I keep official office hours on Monday and Wednesdays at 3 o'clock till 4 o'clock. So you are guaranteed to find me in my office at those times. If you're ever passing by and the door is open and I'm in there, that means you're welcome to come on in if you have a question or if you wanted to talk about something. So anytime it's open, you're most welcome to come in. If you wanted another time and to set it up by appointment, no problem, send me an email and we'll do that. My preferred email is kshoreland@mun.ca. If you email me through Brightspace, I will eventually get it, but I tend to forget to check it. So my MUN email is way faster than my Brightspace email, so there's the one you should try and get me. A couple of social media accounts. When we're working on problems, if you're studying at home and you want me to see your workings, if you use Snapchat, you can send me a picture that way, and it's just a kind of a fast communication tool. Nobody has to use it to be part of this course, but it is one tool that we can use if you want. YouTube channel, for that I mostly post some extra stuff, so extra examples, extra practice, study for the test, so I will have some things up on YouTube. Again, it's completely optional. You don't have to look at those videos, but it's for people who are just looking for a little bit more. Everything in the course will go through Brightspace, so that's where it'll be coordinated. I'm just going to assume everybody here is familiar with Brightspace and how to use it. Anybody has issues, let me know and I'll try and give you a hand. The announcements tool is primarily the way I'll communicate with the class. It will go up as an announcement. It should show up in your notices, so that's where I'll put most things out. Assignments, syllabus, lectures, and notes. The syllabus is posted now. So everybody should have a read through it. I have a handful of paper copies here if anybody prefers to keep a paper copy. So everything is on Brightspace. What's next? The course textbook is University Physics, the 15th edition by Sears and Zemansky or Young and Friedman. So I have the hard copy version. I don't even know if they sell the hard copy in the bookstore. They might sell a paper copy or an e-text. If you buy the e-text from the bookstore, it'll come with a code and you'll have to access it through a Mastering Physics widget on our homepage. If you buy a paper copy, of course, you don't have to fuss about the e-text stuff. We're not going to be using the Mastering Physics assignment system, so you don't have to buy the Mastering Physics code. I do really recommend you get a book, though, and a secondhand book is fine, so a calculus-based textbook. I'll be referring to this specific textbook, so this is a good one to have. We're going to go through pretty much all of these topics. I can't promise we'll get to wave optics, but we'll do our best. You'll probably end up reading some of it at home to supplement what we talk about in class. Okay, just as a reminder already, I'm sorry, those masks got to be right up over your nose, please. Oh, and stop me if you have any questions along the way. Technology requirements. Our assignments are going to be done online through Brightspace, so everybody should have somewhat regular access to the internet. I assume that's not a problem, but just at least once in a while, even if you don't have internet access in your home, if you can pop out to Starbucks or on campus once in a while, that should be enough. Most students prefer to have a laptop or a desktop computer. If necessary, you can do anything related to the course on a cell phone or a tablet. If, heaven forbid, we have to close again due to COVID, I am prepared to deliver the rest of the course remotely. And again, that could all be done from a cell phone if you need to, as long as you get internet once in a while. So the lectures themselves will be right here in this room. I don't see that changing. I am kind of a fan of the lecture capture system. Have most people done a class that had lecture capture? At least some people. This room is not lecture capture enabled, and I couldn't get a lecture capture classroom. So I have a homemade version. I've got an iPad here. It's going to be recording the screen. My headphones, I'm not trying to look cool, I'm using them as a mic pack. The headphones are picking up my audio, and I will post these videos. I know once in a while you might not feel well and not want to come to class. You could have the electrician come in and you have to stay home. I know life happens. So I will be posting these videos, but the quality is not guaranteed. It's just an iPad and my Skull Candy headphones. It's kind of the best I got. Before class, I will always post these blank slides. This introductory material, you don't really have to print this stuff. But as we get into the work, I'll be adding notes to the slides as we go. You'll probably, I recommend that you make notes along with me. There's kind of a well-established connection between making notes and retaining information. So you may find you understand the course better if you make the notes with me. All notes I make, I will post after class as well. So if you miss a few words here and there, no problem. It's all going to be posted. You can compare your notes to my notes and make sure it's complete at the end. And then during class and after class, anytime really, I do encourage you to ask questions whenever they come up. I guarantee if one person is wondering about something, a good third of the class is wondering about the same thing. Okay, next is our evaluation scheme. So everything except for our assignments will all be in person. Labs are worth 15%. The labs have their own Brightspace page, Physics 1051 labs. The labs are in room 2039, that's sort of just around the corner over there in that room. Our lab instructor is Mr. Stephen Campbell. Here's his email address right here. If you have issues with the lab, he would be your first contact. Unless it's something you need to keep private, then of course you can talk to me or something like that. You need to have done the science safety classes. I expect to meet the prerequisites for this class. You've already done these, but if you haven't done them already, you should get them done in the next week or so. You do have to pass the labs in order to pass the course. That's a firm rule in the physics department. If you get 100 on your assignments, you get A's in your term tests, A on the final exam, and 48 in your labs, you actually get a fail in the course. That sounds really harsh, but the good news is it's pretty easy to just pass the labs. If you show up and you don't sleep through them, and you put some pen to paper at some point, you're probably going to get a pass. The really good news, if you show up and you focus, you ask a few questions, you work with your partner, you're probably likely to get good grades in the lab, and you'll find it brings your course marks up. So it's easy to do very well in the labs if you just focus a little bit. We're also going to do problem sets in this class. The problem sets happen during your lab period. So basically you're going to go to the lab every single week. You'll work on some test-like questions during the first hour. During the second hour, there will be a short quiz. That quiz is not going to be as detailed as a midterm exam. It'll be based on the problems you had just been working on. And it's more of a check-in to see how you're doing. Do you understand the basics? So they're not intense, but they will just check. That will be for credit, and it shouldn't take you too long. You know, most people are finished 5 to 10 minutes, that short quiz, even though you get lots of time. So there's that. The assignments are going to be offered through the quiz feature on Brightspace. You click assessments, quizzes, and you'll find your assignments right there. If you need any help with those at all, you can check in with me or drop into the help center. Got 2 term tests, those are the dates. They're going to be in the class time. We're so crowded here that I might see if I can find another spot for us to write, just so we can spread out a bit. So I'm not going to commit to location just yet, but they will be this day and this time. And our final exam is worth 40%. Okay, I'll just pop this up to get us all on the same page. It's a good review. So it's all about academic integrity. And the gist of it is you're not allowed to cheat, and like everybody knows that, right? I very much heavily encourage you to work with other people. I think that's really great. I think it's really good if you work with your classmates, your lab partner. Maybe you have some people who did Physics 1051 before. I think it's a very good thing to work together, because I think a lot of good learning comes when you just deal with things peer to peer. When it actually comes time to put your pen on paper and write down an answer, that's what has to be completely your own work. So you can't look at somebody else's and write it down. You have to gather all of your thoughts and write your own answer. So working together, great. Copying, not so much. To go along with that, any of the class materials or evaluations I give you, you're not allowed to upload them to any website. So Chegg and Bartleby and all of these online pay-per-use sites. If you upload things there, not only is it misconduct, it's also theft of intellectual property. I do track down people who do that, and they do get penalized. And there are legal and academic penalties. So nothing from the class is allowed to go up online. And we have all the help in the world if you want to get it, so you don't need to resort to those sites. This one, another part of the calendar. This may be important this year since we're still kind of in COVID times. If you miss an evaluation because you're ill or feeling a little ill and you can't come to campus, certainly I anticipate that's going to happen for at least some people. Anything you miss, you just have to get in touch with me from your MUN email within 48 hours. If I hear from you after 48 hours, say 50 hours, I'm obligated to give you a 0. Less than 48 hours, then I give you an accommodation. I can't commit to what the accommodation would be right now. It sort of depends on circumstance. But I just need to hear from you within 48 hours. Like, sorry, I'm sick, can't make it to the test. And it's like, okay, let's deal with that. If you're out fewer than 5 days, I don't need any sort of documentation, just your email saying you can't make it. After 5 days, I may need some sort of medical documentation, a note from a doctor or the emergency room or what have you. So 48 hours is sort of the key thing to remember to get in touch. The key resources for help I would recommend, first of all, is CITL. They have a lot of really good stuff, particularly on using Brightspace and some other approaches to studying and learning, so that's really good. The Help Center is in this building. If you've done a physics course with us before, you may or may not be familiar with it. So it's upstairs, room 3071. It's open Monday to Friday. I've written 10 till 3. It might be 10 until 4 some days, but certainly 10 till 3 every day. It's completely free. You go in, you sit down, there'll be 1 or 2 people working there. You just go up, you ask a question, and they'll help you figure it out. You're allowed to ask whatever questions you want. You can ask for help with assignments or studying or just figuring things out. So you can ask anything you want, completely free. You don't have to pay for anything. Here's all of the lab staff. So you might see any of these people here, except Nuri, who just had a baby girl and she's off on mat leave. So next, I'm well aware that Physics 1051 has a reputation for being a little bit of a tough course. Anybody ever hear that before? Yeah, getting a few nods. 1051 is slowly evolving. I think at this point, I've been tinkering with it for about 2 years now. I think we've hit a really sweet spot for really good information, kind of trimmed back the calculus a little bit, lots of physical applications, more circuits applications. So I hope you're not going to find 1051 intimidating. I think it's probably at exactly the right level at this point. And I certainly do believe that everybody sitting here can do well in this class. And I think if you really put the work in it, everybody sitting in this room is capable of getting an A in this course. So if you do the work, I'm quite certain you're going to see the results. So I'd recommend that as best you can, stay on top of your lectures. So come on time, try to focus as best you can, take your notes, ask lots of questions whenever something is confusing, either during class or after class, whatever works best for you. I'll be giving you lots of practice and homework questions during class. Those homework questions, I don't take them in to grade them or anything, but they're your practice for the midterms. The homework questions I give you are like test questions. I'll always give you the answers and the solutions. It's in your best interest to try them without looking at the solutions. That's a good way for you to check in and see how you're doing. So there's going to be lots of work for you to do. Staying organized. I expect most of you are probably doing 4 or 5 courses. Lots of you probably have a job. Probably lots of you have family obligations, and most of you at least would like to have a social life. So I expect you're all quite busy. So I think it's a good idea that you stay as organized as you can. I find a calendar a really good thing. So I would suggest you put in your classes, your labs, your lectures, your tests, your assignment deadlines, when you're going to study, when you're going to the help center. That should really help you stay on top of things and not just forget them, because it's easy to forget stuff because you have a lot of stuff. So I recommend the organization. There's lots of help, so you can work with your friends. I have discussion groups open on our Brightspace page. I always plug them, nobody takes me up on them, but they're there if you choose for this to be the year everybody uses the discussion groups. That is a place where you can talk to each other. You can come see me anytime, and the Physics Help Center is going to be open most of the time. Last is this little bit. So there's a fair bit of pedagogy showing that if you study some every day, it's a good way to master the material. So I offer to you the challenge. If you can keep a physics streak, then at the end of the semester, I will give you a prize. What I mean by a physics streak is you have to do some physics every single day, and I do mean every day. You can't take the day off because you're not feeling well, or because you have a wedding, or because you got friends coming over. So every single day between now and the last day of classes, then I will give you a prize. Okay. This generally spurs 2 questions.
How do you prove?
How do you prove it? So there's question 1 I was anticipating. My answer to that question is, I'm going to trust you. If you tell me you've kept your streak, I choose to believe you're not going to lie to me.
What's the prize?
There's question number 2. There's only one way to find out what the prize is. So I've given away a bunch of these prizes over the years. I've been at this 5 or 6 years now. Every year I do manage to give away a handful. I keep hoping for the year I'll give away 1 to every person in the class. And I do put my money where my mouth is. This is my current streak on Duolingo. I'm trying to do learn French, so I've done some every day for more than 4 years. Quite proud to say when I went to St. Pierre, I got some compliments on my French. So a little every day should help you get where you want to be. Okay, last, maybe the most important, is your own well-being. We kind of have a lot going on in the world right now, and you may face some struggles, and there are lots of ways to struggle. Could be academic, could be health, physical or mental, could be just life issues. If you find you're struggling, there are a lot of resources available to help. I've got a bunch of them listed in the syllabus. Some are online, some are in person. You can always come talk to me. I can fix easy things, like help you set up your textbook. I probably can't fix anything hard, but I can find the person who will help you fix it. So if you're having issues, let me know. I will help the best I can. Okay, that was the zoom through our course introduction. Does anybody have any questions about anything? Good so far? Okay, super. So now what we're going to do is spend the rest of the class doing a review of chapter 14. So how many people did physics 1050? Okay, so lots. How many people do I have jumping from physics 1020, 1021? Okay, also lots. Oh, okay, cool. So if you came from physics 1021 or 1050, this should be a review. If you're coming from physics 1020, this material is going to look new to you. I'm going to do a very fast review. It'll take 20 to 30 minutes. If this is too much and you want more review, I have a longer review on our Brightspace page. So it's kind of a lengthy video with lots of examples, lots of notes, and lots of videos. So if this is not enough of a review, then you can check out our Brightspace page. And this is going to be the jumping point for our chapter 15. We're going to use a lot of this terminology and these concepts when we get started on chapter 15, which we should get to on Friday. So simple harmonic motion, chapter 14. It's the oscillatory motion of an object that moves under the influence of a restoring force. And a restoring force is defined as a force that pushes something or pulls something back towards equilibrium. So the classic example is a mass on a spring. So I put a mass on a spring, I pull it down a little bit, and it bounces up and down. That's simple harmonic motion. There's lots of examples of that sort of everywhere. When it bounces up and down, it oscillates. So there's the oscillatory part. So it goes up and down. So one complete cycle is from one position back to that same position. So say from the top, down, back to the top. That's one oscillation. Things we care about is how do we describe the position as a function of time that turns out to go as a sinusoid, like a sine or a cosine. We care about how long does it take for one oscillation, that's the period. And we care about how many times does it oscillate every second, that's the frequency. So those are the things we're going to talk about here in this chapter 14. One sort of neat little tidbit I learned is that dogs, any dog owners, lovers? When dogs get hot and they pant, they actually pant at exactly the right frequency for their body, the resonant frequency that helps them cool off the most efficiently. So there's a little biology physics crossover that I think is cool. Okay, so let's start to get some notes together on all this. So let's start. Our very first picture on that slide is a spring at equilibrium. So that's just a spring hanging on a stand. When it's at its relaxed length like this, nothing is pulling on it. That's called the equilibrium length. It's at equilibrium, it's not moving. So that's what equilibrium means. There's not much interesting happening right there. So the next thing we do is we take a mass and we hang it off the spring. When I put the mass on the spring, the mass has weight, so it pulls it downwards. So that's sort of the next step in the process. So I put my mass M on the spring. When I put it on, it's stretched down from this point to this point. You can call that distance y. So y is how much it's stretched by. That's measured in meters. Now that my mass is here and hanging more or less still, this is a new equilibrium. So this is the new equilibrium point. So if we draw a line coming across here where our mass is at rest, this point right here is called the equilibrium. And we say y equals 0 at this point. I'm using y here for position because it's a vertical mass on a spring. If it were horizontal, I would use x. So y just indicates the position. So far so good. We can ask what happens when it's here sitting at equilibrium. Well, we know there are forces on it. So it has a downward force of the weight. So the earth pulls down on it. That's the force due to gravity. But the spring pulls back up on it. That's the spring force. And you probably remember that as being called Hooke's law. That's measured in newtons. What the spring force does is it always pulls it back towards equilibrium. So whichever way we push it or pull it, it's always going to push it back to that center point. When it's at rest, we can apply Newton's second law, which will say that the sum of the forces is equal to the mass times the acceleration. We've got our spring force pointing up, so there's our spring force. We've got our weight pointing down. When it's at rest, the acceleration is 0, so the spring force minus mg equals 0. Our spring force is the spring constant k times however much it's stretched by, which we called y. So k is our spring constant with units of newtons per meter. So ky minus mg equals 0. This is when the mass is completely at rest. Something we might do with this sort of a setup is I might grab a ruler and measure how far did it stretched by. I know that's 500 grams, so I could put in my m, I could put in my y, and I could calculate my spring constant. I think that was done in a 1021 lab, so one of the labs in physics 1021, anybody coming from that class. So the next thing we do, because this in and of itself is not super interesting, is we move our mass a little bit and we watch it oscillate. So I might push it up and let it go. Now it bounces up and down. When I pushed it up a little bit, that amount I pushed it up is called the amplitude. So the center goes up to right here. The distance between the equilibrium and how far I pushed it is the amplitude A. Our amplitude A is the maximum distance from equilibrium. It will never go farther than that distance. It's a distance, so we usually measure that in meters. Now it's oscillating back and forth. The furthest distance it goes on top is A, on bottom is also A, so it oscillates back and forth between plus A and minus A. So it could also come down this far. And one full oscillation will take it from here all the way down and up here. So this is one oscillation. Okay, what else do we need? If we want to discuss the motion in simple harmonic motion, we care about what is the position as a function of time. We care about the period, that's our time for one oscillation, that's measured in seconds. And the number of oscillations per second, that's our frequency. Those units are either seconds to the -1 or hertz. If period is time for one oscillation, if frequency is oscillations per second, and frequency is equal to 1 over the period. Okay, so far so good. Any questions? I guess this is kind of review for most people, but new for anybody in 1020. Okay, next. So since we care about an equation for the position as a function of time, let's set it up so that we have a mass m oscillating on a smooth table. When we say a smooth table, we mean a surface with no friction. If we had friction, things would be different. So we're going to say frictionless. And we're going to figure out our equations by solving Newton's second law, F equals ma. So that's where we're going to go with this, and we're going to get an equation for position as a function of time in terms of the numbers we just started with. So we might say that at the very beginning, our mass is at the equilibrium. So here's the definition of our equilibrium length. I'm going to use x for my symbol here now because I have a mass on a horizontal table versus a mass on a vertical spring. So x is going to be my position. My equilibrium is x equals 0. I'm going to take my mass and I'm going to pull it out some distance. That distance is going to be the amplitude. After I pull it out here, I'm going to let it go and it will oscillate back and forth. So I will pull it out to the amplitude. When I've pulled it out to the amplitude, the spring exerts a force on it to pull it back towards equilibrium because that's what spring forces do. So there's my spring force. So in my coordinate system, I'll say to the right is positive x. So to write Newton's second law, says that the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. In this case, I'm holding it here, I'm about to let it go, it's going to move. It's not going to be in equilibrium, it is definitely going to get pulled to the right. So that tells me that I know that my acceleration is not 0, because it's not in equilibrium. Is the pen size and the handwriting okay? People see it all right? Yeah. So let's put in the force I have in the x direction is my spring force to the left. So I've got minus kx equals mass times acceleration in the x. This is the equation I'd like to solve, so I see x equals something. I want an expression for x. If I want to solve this, the first thing I'm going to do is I'm going to remember that my acceleration is related to my position. So when we defined acceleration in Physics 1050, we know that acceleration is the derivative of velocity with respect to time. Okay? It's probably familiar to most people. So acceleration is change in velocity over change in time. But velocity is the derivative of position with respect to time. So let's get that bit in there. That tells us that acceleration is the second derivative of position with respect to time. So let's put this in this equation, and then let's see what is the expression for x going to turn out to be. So minus kx equals mass times the second derivative of position with respect to time. I'm going to rearrange that to say d2x by dt2 equals minus k divided by m times x. So I divided both sides by m. So this equation is actually fairly well known. I would expect maybe you came across this in Math 1001. I'm not sure when you do second derivatives, but I'm thinking this one looks kind of familiar. The solution to this expression is a sinusoid, is a sine or a cosine, because in those equations, the number itself is related to the second derivative of the number. And that's going to be a homework question for you. So this equation has solution. That the position as a function of time is some maximum value a, the maximum value is how much we pushed it out by, times cosine of omega times t, where omega is the square root of k over n. So I remember finding this very dissatisfying when I learned it in math class. The approach was, well, you just have to try it and see if it works. If it works, then clearly it was the right answer. I didn't think that was specific enough for a math class, but they told me too bad, that's the answer, so there you go. So this is the solution to this equation, and there's going to be your first homework or practice question for you to try, is take this expression for x, put it in here, find the second derivative of this expression, put it in here, and see that they're the same thing. See that that solution is true, see that it works. So there's a homework question for you to try. Now what? The last thing we'll do is let's look at this motion and develop a graph. And we know that the graph is going to go as a cosine, and let's think about the different points on that graph. So at the very beginning, we've held it out at the amplitude, and we're letting it go. It's just beginning to move. So at the beginning, it's up at the top. So x is equal to a at the very beginning. And the velocity is equal to 0. And here we might remember that v is equal to the slope of the position versus time graph. So that's something that's going to be important. As we let it go, it's going to move to the left because there's a force on it pulling it to the left. Because it's moving left, there's a force to the left. It's going to speed up. It's going to get faster and faster. It's going to keep speeding up until it hits this equilibrium position where x is equal to 0. So the place it gets to next is the equilibrium. It speeds up the whole time it's approaching there, so when it gets to here, the speed is a maximum. So at this point v equals 0, at this point v equals maximum. It's going to keep moving to the left because it's moving left. The force is going to pull it back towards equilibrium. The force pulls it to the right, so it's going to slow down. Eventually, it's going to come to a complete stop when we hit x equals minus a. And then we repeat on the way back. Speeds up towards equilibrium, slows down past it, and it oscillates back and forth between plus and minus a. These points here, where v equals 0 at the amplitude and the negative amplitude, these are often called the turning points of the motion because this is where the motion turns around. So that might be a familiar term as well. So x equals plus or minus a, where v equals 0, are turning points. Okay, questions? All good? Okay, excellent. So the next thing you'll see in the notes, if you printed them off or opened them up, is homework questions. So one of them says, prove that thing we were just talking about. And the next one gives you some numbers and asks you to look at that motion. So that'll be a question for you to try. I will post the answers. And I'll get this stuff all posted, you know, by the end of the afternoon today, so it is going to go up right away. Okay, next, let's look a little bit more at that graph and think about that a little bit more. So our oscillation goes back and forth between the amplitude and the negative amplitude. The shape of that graph is a cosine. We just showed that the solution to the equation was a cosine graph. To go from the amplitude back to the amplitude again, we said that was one complete cycle, one oscillation. That means it takes a time of one period to travel that distance. So to go from the amplitude back to the amplitude takes a time t. Okay, likewise, if you said from the negative amplitude back to the negative amplitude, that's also the period. Or if you went from an equilibrium back to the same equilibrium, also the period t. So any one point back to the same point, that's the period t. So how does this t fit in with the equation we just wrote down as the solution? Let's see how period fits in there. So we found from solving Newton's second law that the position as a function of time was the amplitude times the cosine of omega times the time t, where omega was the square root of the spring constant divided by the mass m. It might be important to point out here, this applies to a mass on a spring. K is the spring constant, so we're talking about a spring system here. That's kind of important there. We'll get different kinds of omegas depending on different situations. So this is an equation we got from solving Newton's second law. But there is another way to write down a representation of this graph, a cosine that varies over a period of t. It would also be valid to write that x as a function of t is equal to a times cosine of 2 pi divided by the period times the time. So that's just as valid a way to describe this motion. So then if we compare these two equations, so a is a, little t is little t, means omega must be 2 pi over the period. So just by comparison, we know that that's our omega. So our conclusion is that omega is equal to 2 pi divided by the period. Here we might remember that we said frequency was 1 over period. So this would be the same thing as 2 pi times f. And we already said that that was equal to the square root of k over m. Since omega is 2 pi over t, that's the same thing as angular velocity or angular frequency that you learned about in circular motion. So this omega, 2 pi over t, is the angular frequency of the motion. And sometimes instead of saying angular frequency, we say angular velocity. Those two terms are interchangeable. The units of angular velocity, or angular frequency, are kind of funny. Typically we say radians per second, and the radians comes from the 2 pi, because pi is in radians. But radians is not really a unit. That's just a reminder that we're talking about pi. So you can use radians per second, or just seconds to the -1. Both of those are perfectly valid, and they're equivalent, because radians is not truly a unit. It's kind of dimensional. Okay, the last tip comes with saying that it's radians per second. And the tip is this is really important. Your calculator has to be in radians mode. So everything we do in chapter 14 and 15 and some of 16, your calculator will be in radians mode. I often get the question, how do I know should my calculator be in radians or degrees mode? I think it's a decent question. And my answer to that typically is just kind of a practical answer. If you see the little circle that symbolizes degrees, that's degrees mode. Otherwise, it's radians mode. Okay, so that's just kind of a rule of thumb if you're in a panic in a test and you can't remember. But all of this stuff will be radians mode. Okay, so there's our position as a function of time. And that describes the motion. When you have to, on a test or an assignment or a quiz, if you're ever asked for what is the equation of motion, this is what I'm talking about. It's the equation for x. Okay, so you kind of have to know that's what I mean by equation for motion or equation of position. So it's always the equation for x. So while x is the one we'll talk about the most, velocity and acceleration are also important descriptors of the motion. So let's take our equation for x and let's find our equations for velocity and acceleration using the derivatives. So that's the next thing we'll look at. So our equation for x was a cosine omega t, where omega was 2 pi over t, or root k over m. If we wanted to find the velocity, then our velocity as a function of time is the derivative of position as a function of time with respect to time. So we're doing d by dt, a times cosine omega t. I'm going to assume that everybody's pretty familiar with derivatives. I'm going to go through the derivatives a little bit quickly. If it's too fast and you have a question, please kind of stop me, but I don't want to take forever because I figure you'll just be bored. So let me know if I'm going too fast with the derivative stuff. So the first thing we can do is take our a outside. Next thing we have to do is take the derivative of cosine. You may remember, or you may have to look up, when I give you a test or a final exam, I'll either give you an equation sheet or let you bring in a sheet of notes. You're not going to have to remember these derivatives. I kind of only really expect you to remember power law stuff. And mostly that's because I can't remember these things very well. I look them up pretty frequently. So the derivative of cosine is minus sine. And then we have to do the chain rule, which says we have to take the derivative of the argument, omega t. The derivative of omega t, there's a power law, is just omega. So we get that our velocity of function of time is our minus times a times omega times sine of omega t. So doing our derivative of x gets us an equation for the velocity as a function of time. Let's kind of have a look at this. So our velocity equation is sinusoidal, so it changes sinusoidally just like x did. So it goes back and forth in a periodic motion. Our velocity, when t is equal to 0, our velocity is equal to 0. So that matches the motion we talked about. So v of 0 equals 0. What else? Our sine has omega t, so it's sine of omega t. That means it's periodic with exactly the same period, because omega is 2 pi over t. So if we look at our velocity graph, it has exactly the same period as our position graph. Okay, so same period. What's a little bit interesting here, sometimes throws people for a loop, is it has a different maximum and a different minimum. Okay, so our x graph was measured in meters, or sometimes centimeters. Velocity is not measured in meters and centimeters, so it's going to have a different maximum or minimum. How do we find the maximum or minimum? Well, we think about the nature of sine. We know sine oscillates back and forth between plus and minus 1. That'll let us figure out the maximum or minimum velocity. So if sine of omega t equals plus 1, then our velocity is equal to minus a times omega times 1, minus a omega. So that's our minimum velocity. If sine omega t is equal to minus 1, then v is equal to minus a omega times minus 1, and v is equal to our maximum value, a omega. So that would be our maximum, a omega. And this would have units of meters per second or centimeters per second. Okay, so there's our velocity. This equation comes in pretty handy. We'll use that for a bunch of things. Okay, questions? Okay, I think we should have enough time to get through our acceleration equation too.
What's that little note underneath the AW and the box?
This right here?
Yep.
That's just my name.
Oh.
Copyright Kelly Shoreline. Okay, looks like we're good on it. Okay, so this is just the same slide again. I printed it a second time to give myself more room because I thought it was going to get messy. So here's our velocity equation. There was our Vmax. There's the graph. Our acceleration is the derivative of velocity. So let's get going with that one. A of t equals d of t by dt. So the derivative with respect to time of minus a omega sine omega t. So my minus a omega come out front. I get d by dt of sine omega t. The derivative of sine omega t. Sine goes to cosine when you do the derivative. And you got to do your chain rule again and you get omega. So I skipped through this one even faster than I did last time. So my acceleration as a function of time is minus a times omega squared times cosine omega t. For my acceleration graph, you see that we get the same period again because it goes as cosine omega t and omega is 2 pi over the period. So it's same period. My starting point, if t is equal to 0, cosine omega t is equal to 1, and a is minus omega squared, a omega squared, so it starts down at the minimum. For my maximum and minimum values, if cosine omega t is equal to plus 1, then my acceleration is minus a omega squared. If my cosine omega t is equal to minus 1, then my a is equal to plus a omega squared. That's my maximum acceleration. And acceleration is either meters per second squared or sometimes centimeters per second squared. The last sort of useful equation, sort of interesting equation, I think I'll move over here a little bit. A of t is equal to, and I'm just going to write this one a little bit different. I'm going to pull my omega squared out front, minus omega squared times a cosine omega t. So I just swap my omega squared to my a. You might notice here, this is the equation for x. So the acceleration as a function of time is minus omega squared times x of t. That can be useful as well. So the acceleration is related to the position. You know, the position at any time, you can find the acceleration at any time just by multiplying by minus a omega squared. Okay, I do have one more slide in this review, but I don't think 60 seconds is going to cut it. So let's stop there and we'll finish next time. That clock is usually off, and I'll try and go by cell phone time.